Now we're going to look at Doppler ultrasound. The Doppler effect occurs whenever echoes come from moving targets. They may be scatterers or they may be reflectors. And we may be talking about moving blood or moving tissues. Whenever there is movement of the targets, the echoes coming back from those targets will have very slightly different frequencies to the transmit frequency. That difference, that change of frequency due to the motion, is called the Doppler shift. The machine can detect the Doppler shift and measure it. The Doppler shift is proportional to the speed of motion of the targets, but it's not just their absolute speed, it's the speed at which they are moving towards the probe or away from the probe. That's very simple, of course, if the motion is actually directed straight towards the probe or away from the probe, but it becomes more complex when the motion is in any other direction. So as I said, the machine can detect this Doppler shift, analyze it and display it. There are three different kinds of Doppler instrumentation which I'll be describing. The first and simplest of those is continuous wave Doppler. The next is pulse Doppler, and then we have color Doppler. Here's the basic idea. First, if we think about a stationary object, then if the transmitted frequency is f, the echoes coming back from that object will also have a frequency of f. There will be no Doppler shift. Now, in this second diagram, I'm showing an object moving directly towards the probe with a speed v. In this case, the received echo will have a frequency that is slightly higher than the frequency that is transmitted, and I'm calling that f with a subscript d, and that's the Doppler shift. Now, as I said, things become a little more complex when the motion is in some arbitrary direction, not directly towards the probe or directly away from the probe, and so that's what I'm showing in the right-hand side here. So we have an object, let's say it's a red cell in blood, moving in the direction I've indicated with the arrow labelled V. Now, as I said, the Doppler shift is determined by how quickly that is moving towards the probe. And to calculate that, we have to multiply the velocity by the cosine of what we call the Doppler angle, theta. So I've indicated that the Doppler angle is the angle between the direction the object is moving and the beam direction. So we need to know that angle in order to quantitate velocity from Doppler measurements. So again, the speed at which this object is moving towards the probe is v cos theta. So here is the full Doppler equation. It says that the Doppler shift is equal to 2 times the ultrasound frequency f multiplied by v cos theta, and all of that is divided by the propagation speed of ultrasound in soft tissue. If we put in standard sorts of numbers, typical numbers, we'll find that the Doppler shift typically falls between about 0 and 15 kilohertz, which by sheer good luck is within the range of frequencies we can listen to. Now you'll notice I've indicated that the Doppler angle should be between 0 and 60 degrees, and I'll discuss very shortly why that is so. So on the left-hand side, I've shown a graph indicating the Doppler shift, and that's the green lines and the vertical axis, and I'm showing it as a function of the Doppler angle, which is on the horizontal axis. When the Doppler angle is 0, that means the flow direction is parallel to the beam. Echocardiography is the one area where this is a fairly common situation. In many other applications, it's quite impractical to try to achieve that situation, and indeed angles more like 60 degrees are very common. So what you can see is that the Doppler shift falls. It falls slowly at first as we go up from 0 degrees, but then more rapidly until when we reach an angle of 90 degrees, where the flow is perpendicular to the beam direction, there is no Doppler shift. Now, as I said, the machine is going to be detecting and measuring Doppler shift, And we will then want to be able to calculate blood velocity from Doppler shift. So we'll be using, or the machine will be using, the Doppler equation to do that. In order to do that, it needs to know the value of the Doppler angle theta. I'll show you in a minute that the user helps the machine to determine what theta is, but there's always going to be a certain amount of judgment and estimation in that. And so the value the machine uses to calculate velocity from Doppler shift is likely to be wrong by a few degrees. This graph shows the impact of that on the accuracy of the machine's calculation of blood velocity. What I'm assuming here is that there's a 5-degree error in the determination of the Doppler angle, and that's probably quite a realistic value. So if we look first at the left-hand side of this graph, you can see that when the Doppler angle is 0 or close to 0, there's very little error. But if we're at 60 degrees, you can see on this graph, then that will induce a 15% error in the measurement of the velocity. And that's normally regarded as about the maximum tolerable error in that measurement. And therefore there's an international agreement that an angle of 60 degrees is about the maximum acceptable angle. Now, one other thing I need to talk about is the scattering of ultrasound by blood. Now, we know from looking at grayscale images that blood is normally echo-free in an image. And so this indicates that the scattering from blood, which is almost entirely from the red cells in the blood, is very, very weak. To compensate for this, when the machine is making Doppler measurements, it increases the transmit power. So each transmit pulse has greater energy than for grayscale imaging. Now, the machine could do this by increasing the amplitude of the transmit pulse, but that would not be good from a safety perspective, and therefore instead it increases the duration of the transmit pulse when it's doing Doppler. So there's going to be a greater transmitted intensity due to this compensation for the poor scattering. The other thing to consider is that continuous wave Doppler and pulsed Doppler both require the ultrasound beam to remain stationary. It doesn't scan backwards and forwards through the tissues, creating 2D information. It is stationary, collecting Doppler from one point or along one line. And this means that all of the transmitted energy is concentrated in a small amount of tissue. And so the combination of these two factors means that exposure levels from Doppler are significantly higher than exposure levels due to grayscale imaging. Now, the other implication of the poor scattering of blood is that we need to be concerned about strong Doppler-shifted echoes coming from the moving tissues that are normally nearby when you're looking at moving blood. So arterial walls move quite dynamically, and of course cardiac walls and other cardiac structures are very dynamic. Those moving tissues will produce Doppler-shifted echoes that will be much stronger than the Doppler-shifted echoes that we're interested in coming from the blood. So the machine has to do its best to suppress these Doppler-shifted echoes coming from moving tissue. This is done by something called a wall filter. Luckily, the tissue motion is significantly slower than the motion of the blood, and so the machine can simply filter out low Doppler shift values. So basically the machine is going to remove low Doppler shift frequencies from the Doppler signal, and then we will get the signal that is predominantly from moving blood. The Doppler signal comes from a volume, which we refer to as the sample volume. The red cells within that volume will not all be moving at the same speed. That's the nature of a fluid, that different parts of the fluid move at different speeds, and therefore there will be a range of red cell velocities within a sample volume at any one time. The result is that at any one time there will be a range of different Doppler shifts detected. For this reason, the machine takes the Doppler signal and breaks it down into its frequency components and displays that as a spectral plot as a function of time. So here's an example. We've got a linear probe looking at a radial artery. The operator has used color Doppler to find the radial artery and to decide where they're going to position the sample volume. The machine then indicates with a white line where the beam is going to point in order to get Doppler signal from that particular volume. So you can see the white line at an angle. You, the operator, can change that angle, if necessary, to make sure the Doppler angle between the beam and the flow direction isn't more than 60 degrees. So you have control, at least with linear probes, to steer that beam around in different directions for both color Doppler and pulse Doppler to get a suitable Doppler angle. You can see that the line indicating the beam direction has an area in the middle of it where it's interrupted, and that's where the sample volume is. You'll also see that there is a short line which has been aligned parallel to the blood vessel. I refer to this as the angle cursor or angle marker, and the operator rotates it so that it is parallel to what they believe is going to be the flow direction. The machine knows the direction it's pointing the beam in, and therefore it can calculate the Doppler angle. The machine also can determine the depth that the sample volume is sitting at, and therefore it knows how to acquire echo signals from that particular depth. The Doppler signal then that's acquired from that sample volume is displayed down the bottom in the spectral display. So you can see about 5 seconds of spectral tracing here. The vertical axis is Doppler shift, but you'll notice that the machine is reading that out in centimeters per second. So the machine is converting Doppler shift values into the corresponding velocity values using the Doppler angle that it's calculated. You'll notice that the user has made a measurement at one particular point. There's a small X on the top of one of the systolic peaks. And in fact, there's a second marker point at the end diastolic part of that same heart cycle. So they're measuring both the peak systolic velocity and the end diastolic velocity. Those values are in fact displayed in the upper left of this slide. So I've just briefly explained the Doppler principle and shown you the Doppler equation and explained that the machine measures Doppler shift and it calculates V cos theta. And then if you angle correct using that cursor, then the machine can calculate velocity from the Doppler shift. I've emphasized that you always need to make sure that the Doppler angle is 60 degrees or less. I then talked about the fact that blood is a weak scatterer, and there are some implications in terms of both transmit power and also the need to filter out Doppler signals from moving tissue. And finally, I talked about the spectral display, and what we're going to see is that this is used for both continuous wave Doppler and pulse Doppler.